We're now going to use the concept of propagation of uncertainty or propagation of error to work some example problems. All right, the first example is a straightforward problem of power measurement. From previous classes in physics, you probably know that to compute the power of an electrical circuit through a purely resistive electrical circuit, we need to know the voltage and the current, and we need to take the product of the voltage and the current to determine the total power. Here, we say that we know that the voltage and current have been measured with a 99.9% confidence interval to be 100 plus or minus 2 volts and 10 amps plus or minus a tenth of an amp. And what we want to do is we want to calculate the maximum uncertainty in the power measurement and the best estimate of the uncertainty in the power measurement. We know that if we take the product of the voltage and the current nominal value, we should get 1,000 watts, or 1 kilowatt. Now, we need to apply the partial derivative approach to come up with the uncertainty in that measurement. Okay, and here's how we're going to do that. All right, so again, we know that power is the product of current and voltage, and that's going to give us 1,000, so that's our nominal value. We also know the uncertainty in the current, W sub I, right here, is 0.1 amp, and we know that the uncertainty in the voltage is 2 volts, plus or minus 2 volts. Okay, so to calculate the uncertainties, we're going to need to take the partial derivative of the function with respect to each of the two measurements that were made. Okay, so we know power is equal to current times voltage. So we need to take the partial derivative of power with respect to current, and we have to take the partial derivative of this power function with respect to voltage. So taking the partial derivative of power with respect to current, what we're going to do is we're going to assume that current, I here, is a variable, and that everything else in the equation is just a constant. All right, so if we take this I to be a variable, and we take the derivative of this variable right here, what we wind up with is the derivative of something raised to the first power would be something raised to the 0th power, or 1. So the result here of the partial derivative of power with respect to current is voltage, V. All right, and we apply the same logic to come up with the partial derivative of voltage with, the partial derivative of power with respect to voltage being equal to current, which is 10 amps. Then what we're going to do is we're going to apply this formula for the maximum uncertainty. So the maximum uncertainty says that I'm going to take the partial derivative of power with respect to current and multiply that by the uncertainty in the current. All right, so that means I'm going to take this 100 and multiply it by 0.1. I'm going to take the absolute value of that, so that is this part right here. Okay. Then I have to repeat that with my voltage measurement. So my voltage measurement, I'm going to take the partial derivative of the power with respect to voltage, which we said was going to be current, or 10 amps. And I'm going to multiply that by the uncertainty in the voltage measurement, which is 2 volts. I'm going to take the absolute value of that. I'm going to take each of these terms and add them together, and that gives us a maximum uncertainty of 30 watts. So we would say that the maximum uncertainty with 99.9% confidence is 1 kilowatt, or 1,000 watts, plus or minus 30 watts. We can repeat the same thing now using the most likely uncertainty estimate. And the only difference here is that what we're going to do is take each of these terms that we computed up here, and instead of taking the absolute value, we're going to square each of those values, add them together, and then take the square root of that total sum. And that's going to give us 22.4 watts as our most likely uncertainty estimate. So again, we would state the power measurement here as being 1,000 watts plus or minus 22.4 watts with 99.9% confidence. Okay. Now I know in other classes you have probably seen or are familiar with this relative uncertainty equation. And I wanted to bring this up because I know I've heard that people say things like you want to take delta I over I plus delta V over V, or the uncertainty in the current divided by the current, and square it, and then add that to the uncertainty in the voltage over the actual voltage and square that. All right, and what we find out if we do this method is that we get a relative error or a relative uncertainty of 2.24%. Well, 2.24% of 1,000 watts is 22.4 watts, which is the same uncertainty that we calculated using the partial derivative approach in the previous slide, right? 22.4, and using this much easier relative uncertainty equation, we come up with the same result. But this works in this example only, or in similar examples, but it doesn't work all the time. So the reason that we have to employ the partial derivative method is because the partial derivative method always works. I know it's a pain, I know it's not what you want to hear, but the partial derivative uncertainty method always works. The relative uncertainty method works only if all of the terms in the equation are multiplicative or multiplied and divided. If you have any addition terms whatsoever, or you have square root terms or things that are squared, this relative uncertainty approach does not provide the correct result. Just taking the uncertainty and dividing by the nominal value and squaring it, the relative uncertainty will not work in cases where you have any additive terms or any terms that are squared or have a square root in them. Okay, so please be careful with that, and understand that while the relative uncertainty method is very convenient, it's only valid if everything is multiplied together and there are no other terms, no other operations, mathematical operations occurring.